Good morning. Welcome to my video class. Today we are discussing the chapter Current Electricity. So this is the third chapter in your plus 2 textbook. So in the first chapter there we have studied the nature and the properties of electric charges that's in rest. But in this chapter we are discussing about the electric charges that's in motion. As the name indicates, these moving charges constitute electric current. So before coming to the title electric currents, we want to know what is a current. When you are looking to your surrounding, there you can see different types of currents are there. Flowing water, wind are some example for these kinds of currents. When you come to water current, there you can see the water is always flowing from one point to the another point. Who will decide the direction of flow of water? Definitely, as you have studied, the potential level, the potential energy decides the direction of flow of water. Always the water is flowing from higher potential to the lower potential or higher level to the lower level. In the case of wind, there you can see air is flowing from high pressure region to the low pressure region. That is, so when you are analyzing these two currents, there we can see some factors there which decide the direction of flow of particles. Similarly, the electric charges are flowing from one point to the another point. So these flowing electric charges constitute electric currents. In this chapter, in details, we are discussing about this electric currents. Such a current occurs in many situations. Lightning is one example for such a current. During the lightning, electric charges are flowing from cloud to the earth through the atmosphere. But in lightning, the flow of charges are not steady. In our day-to-day life experience situations, there we are dealing with many devices where we are getting a steady flow of electric charges. For example, a torch, a cell-driven clock are some example for this. In this chapter, we are discussing about the steady electric current and some laws which governs the steady electric currents. Before coming to these facts, we want to know what is an electric current. Now, let's assume a closed surface which contains large number of positive and negative charges, and these charges are in a random motion. Now, let's divide this closed surface by using a vertical plane. Now, just divide this closed space by using a vertical surface through which the electric charges cannot move. Now, here I am making a small window at the center of this vertical plane. Now, the electric charges can move through this window in the forward and backward direction. Now, let's consider Q plus F is the positive charges flowing in the forward direction, that is left to right, and the positive charges flowing in the backward direction can be taken as Q plus B. Q plus B means positive charges flowing in the backward direction. So from right to left. If so, we can say the net positive charges flowing in the forward direction can be written as Q plus F minus Q plus B. It can be taken as Q plus. Now, the negative charges flowing in the forward direction can be taken as Q minus F, and the negative charges flowing in the backward direction can be taken as Q minus B. If so, the net negative charges flowing in the forward direction Q minus is equal to Q minus F minus Q minus B. Then the net amount of charge flowing across the area in the forward direction in the time interval t can be written as Q is equal to Q plus minus Q minus. If so, the quotient Q by T can be defined as the electric current, and that can be written as steady current I is equal to Q by T. Now, the electric current is not always steady, and hence more generally we are considering the instantaneous value of electric current. So how can we define the instantaneous value of electric current? Assume if delta Q be the very small charge, it is flowing through a conductor for a very short time interval delta t. Then we can define the instantaneous value of electric current I of t as I of t is equal to limit delta t tends to 0 delta Q by delta t. So more generally we are using this expression for electric current because in most of the situation the electric current is not steady. Now the SI unit of electric current is ampere. When an electric field is applied on an electric charge, what happens? Definitely the electric charge experiences some force. Due to this force, it will start to move and contribute electric current. However, in atoms or molecules, though the negatively charged electrons and the positively charged nucleus are very strongly bound together, and the electrons are not free to move even if we applied an electric field. But there are some other materials like metals, there are some free electrons are there, and even when we apply an electric field on it, these free electrons will experience a force, and due to that force these free electrons will move and contribute an electric current. These kind of materials are named as conductors. So what is the property of a conductor? In the conductor, there you can see some free electrons are there. Even if we apply an electric field on it, these electrons will experience a force and they will start to move, or that electron will start to move and it will contribute electric current. So that is the peculiar property of conductors. So in this topic, we are discussing the electric current in conductors. As I said, if we consider the electric current through a solid conductor where the electric current is carried by the negatively charged electrons. But there are some other type of conductors like electrolytic conductors. In electrolytic conductors where the positively charged and negatively charged ions can contribute the electric current. But in this chapter, we are restricting ourselves on the topic electric current through the metals. Now let's take the first situation where there is no electric field is present on the conductor. Even if there is no electric field, electrons are in motion due to thermal energy. In this situation, the average number of electrons flowing in one particular direction will be equal to the average number of electrons flowing in the opposite direction, which means these two will cancel each other and there is no net electric current if we are not applying any electric field on a conductor. Now let's see what happens when an electric field is applied to a conductor. For this, just consider a cylindrical conductor of radius r. So this is the cylindrical conductor and the radius of the cylindrical conductor is r. And now take two cylindrical dielectric of the same radius, and one is positively charged and the other is negatively charged, and place these two cylindrical dielectric at the ends of this cylindrical conductor. So here I am placing the positively charged dielectric at this end and the negatively charged dielectric at this end. And these two dielectric placed at the ends of the cylindrical conductor will create an electric field in between the ends of the conductor, and the direction of that electric field is from positive to negative. Due to this electric field, the electrons starts to move from minus Q to plus Q, and that will contribute an electric current. So this electric current will exist until the positive charge gets neutralized. If we have a mechanism that will contribute fresh charges to the ends of this conductor, what happens? The electric field exists for long time, which means we have a steady electric current for long time. Cells, batteries are examples for such kind of mechanism. And we will study about this kind of mechanism in the end of this chapter. Now in the next topic, we are discussing about the steady electric current which is due to a steady electric field. Now let's move to the next topic. A basic law regarding the flow of electric current through a conductor was developed by George Simon Ohm. As an honor to him, this law was named as Ohm's law. Let's assume a current I is flowing through a conductor. Let V be the potential difference between the ends of the conductor. Then the Ohm's law says that the potential difference is directly proportional to I. So here we have to express this Ohm's law mathematically as just here I am replacing this proportionality symbol with equality symbol. So when we are replacing the proportionality symbol with equality symbol, we have to multiply the RHS of this relation with a constant. So here R is the constant, so we have to write this as V is equal to R into I. Here, so this is the mathematical expression for the Ohm's law. Here R is the resistance of the conductor. So here resistance is the one of the fundamental property of a conductor. So hereafter we are coming to the term resistance. Now from the mathematical expression of Ohm's law, we have to write the resistance R is equal to V by I. So this is the mathematical expression for the resistance. You are already studied about the resistance in your high school classes. As you know, resistance is the fundamental property of a conductor. Now we are discussing what are the factors that influences the resistance of a conductor. As you have studied on the first factor, the factors influences the resistance. As you have studied in your high school level, there we know three factors are there that influences the resistance of a conductor. First one, the nature of the material. And the second one is length of the conductor. As you know, the length is directly proportional. As you know, the resistance is directly proportional to length, which means when the length increases, the resistance will also increases, and if length decreases, the resistance will also decreases. Now the third factor that influences the resistance of a conductor is area of cross section. So here the resistance is inversely proportional to the area of cross section, which means when the area of cross section increases, the resistance will decreases, and vice versa. So these are the three factors that influences the resistance of a conductor. Now we have the resistance is directly proportional to length and the resistance is inversely proportional to the area of cross section. If we combine these two relations, we have to rewrite this as resistance is proportional to length by area. So here I am rewriting this relation as an equation. So as we said in the earlier section, when we are replacing this proportionality symbol with equality symbol, we have to multiply the RHS of this equation with a constant. So here I am multiplying the RHS of this equation with the constant rho. Thus we have to write this as R is equal to rho into L by A. Here rho is one of the peculiar property of the conductor named as resistivity. From this equation, we have to write the resistivity rho is equal to, we are rearranging this equation. When we are rearranging this, we will get resistivity rho is equal to R into A by L. So this is the mathematical expression for the resistivity of a conductor. So this equation says that the constant of proportionality rho, the resistivity, does not depend on the dimension of the conductor. It only depends on the nature of the materials, which means this is one of the fundamental property of a conductor. Now we have R is equal to rho into L by A. When we substitute this equation in the expression of Ohm's law, what we will get? So as per Ohm's law, we have V is equal to R into I. That means when we are substituting the value of R in this Ohm's law, we will get V is equal to rho into L by A into I. Here I am introducing a new term, that is current density. What is current density? As the name indicates, current density is the current per unit area. So we have to write current density is equal to current per unit area. So that can be represented with the letter J. So the unit of current density is equal. The unit of current density is the unit of current, that is ampere per the unit of area meter square. So the unit of the SI unit of current density is ampere per meter square. So let's substitute this in this equation. So we have to rewrite this equation as the potential difference V is equal to rho into, instead of I by A, we have to write the current density J, rho J into L. So now we have the potential difference. Now we have to rewrite the Ohm's law as V is equal to rho into J into L. Here rho is the resistivity and J is the current density and L is the length of the conductor. If E is the electric field through the conductor of length L, then the potential difference between the ends of the conductor V can be written as V is equal to E into L. Then the above equation can be written as EL is equal to rho into J into L. Here the L and L will be cancelled, so we have E is equal to rho into J. From this we can write the current density J is equal to E by rho applied, and rho is the resistivity of the material. So here I am introducing another new term, that is conductivity. So what is meant by the conductivity? Conductivity is the ability of a conductor to pass the electric current through it. So here the conductivity that can be represented with the letter sigma. So we have to write sigma is equal to 1 by rho. Is the just reciprocal of the resistivity. That means it is just opposite to the resistivity. So we have to write the conductivity sigma is equal to 1 by rho. So when we are replacing this, when we are applying this into this equation, we have to write the current density J is equal to sigma E. That means the current density J is equal to conductivity into electric field applied in between the conductor. So today, here I am stopping this video class. So in the next video class, we will discuss the further topics regarding this chapter. Thank you.